you, Matt, for inviting me to come and share some ideas today. I always like these opportunities. It's a good excuse to get away from the office and away from the computer screen and to chat to people. And I'm going to kind of, I guess a little bit selfishly, although I guess today's about sharing ideas. So I'm going to, rather than tell you about loads of stuff that we've done and proved and lots of work that's been done in the past, I'm just going to share some ideas. And a lot of this is kind of work in progress stuff. And part of it, from a selfish point of view, is because I'd love to get some feedback from you. If you think, actually, that's never going to work, stop going down that road, please come and speak to me afterwards. Or if you think that's a brilliant idea, that's definitely something you should be investing in. We're still at the point in developing some of these ideas where we could kind of tailor the direction of this. So I've got an interesting job in that I'm kind of, in some senses, your kind of standard university academic, doing work mainly in CFD and the application of CFD to the design process. But I also wear a second hat because I sit on the design team for the Bloodhound supersonic car. So Matt gave me this title, Uncertainty in Automotive CFD, and I didn't really think too much about it until last week when I was thinking about what I was going to talk about, and realised, well, I mean, Bloodhound SSC, okay, it is a car, it's got 4 wheels, there will be a driver, and we're always told we must refer to Andy Green as the driver and not the pilot. But really, a lot of the technology that we've been developing for this project and have applied to this project comes from an aerospace background. But as you'll see later on, certainly in the second half of what I want to talk about, kind of applications of some of these ideas spread across many sectors. So the problem we were set 10 years ago now, for those of you who've been following this project, that's how long we've been plugging away at this, was, I mean, question number 1, that Richard Noble, the project director, came to the university and said, can you answer this question? You've got 12 months to do it. Question 1 is it possible to take a vehicle of roughly these sort of dimensions and have it travelling across the surface of the Earth a few inches above the ground? You must have 4 wheels, there's going to be a human on board. Can you do that safely? Can you do it in a predictable, stable way? Yes or no? You've got 12 months. So that was kind of my first post-PhD role as a postdoc researcher, was to run suites of CFD models of various geometries. This was the starting point that we were given by the initial design team, and over the space of that year we evolved the design to this configuration here. And over the last few years, that design has been optimized to get us to this car here, which is the car that's now built and sits a few miles west of us at Avonmouth at the technical centre. We've finally got the car built. We start the test program next month, so this thing is going to become reality. But in terms of uncertainty, the fastest, in 2007, still to this day, the fastest a car has ever rolled across the surface of the Earth is 763 miles per hour. That was the Thrust SSC car that Andy Green drove back in 1997. So there were, and still are, massive questions about what happens in that gap between 763 miles per hour and our target speed, which is 1,000 miles per hour. And we've been living in this world, which for me as an academic is fascinating because there's lots of questions. From a kind of practical, I'm about to put one of my good friends now, Andy, in this car, a kind of nerve-wracking question because there is so much uncertainty about what happens and to what extent can you accurately model the kind of phenomena that we will be experiencing in this kind of regime of uncertainty above the speed of sound. So over the years we've been applying a range of CFD methods, some fairly standard kind of Navier-Stokes finite volume techniques that you might apply to a conventional aerospace application to this. But we've also been developing, I guess, more novel models. So one of the things that we know is going to affect the ability of our models to accurately represent the behaviour of the car is the fact that the car won't be running through air, pure air. It will have a soup of particles and dust being entrained into the flow around the car. So one of the models we've developed specifically for this application is a high-speed particle entrainment model. The problem we have is no data exists about how supersonic rotating wheels interact with the kind of surface we're going to experience on the Hack-Scheme Pan in South Africa, how much of these particles will get entrained into the flow, and one of the things we've noticed already from running these models is the assumptions you make about the amount of particles that get entrained into the flow have a big influence on the prediction of the models. And I was reading, I think it was one of the recent Innovate UK publications about uncertainty, and I came across this quote, and I thought that does summarise a lot about what we've learned over the last few years, It's the statistician George Box who said all models are wrong, some are useful. And the question we're now trying to answer as we move into the vehicle testing phase is, how can we, as we go through the test program, slowly, you'll be glad to hear, we're not going to go to South Africa next year and just tell Andy, here's a 1,000 mile per hour car, just put your foot down, let's see what it can do. We will be slowly stepping up the speed of the car, initially doing runway testing here in the UK, and then the high-speed test program in South Africa. And how do we try and understand which of the models, and importantly, which settings within those models are providing us the best representation of reality and best match the data that we get back from the car. And the way we're planning to do that, I guess, is a fairly pragmatic approach, which is to try and understand the sensitivities in our model predictions to what I can refer to as the uncertainty space that we have within the modelling. So we know that the kind of things we get back from our models, the lift predictions, the drag predictions, the pressure distribution over the surface predictions, are a function of what turbulence model you choose within your random solver, the fudge factors within those turbulence models, the parameters that you can vary within those turbulence models, the type of scheme we use to stabilize the code for these high speeds and shock predictions, the assumptions we make about the particle entrainment rates in our particle entrainment modeling, we know affect the model predictions. The orientation of the vehicle, all of the design work was done with the vehicle set at some standard ride height and pitch configuration. Basically, we were running the models, changing the geometry to decide to answer questions like, is that better or worse? Has the drag gone up or has it gone down? Has the lift gone up or has it gone down? Now we're starting to think more about, well, in quantitative terms, how accurate are these models? Well, actually, we're now having to think about, well, to what extent does pitch and ride height affect these solutions? And then other factors that we maybe understand a little bit better, like mesh resolution. To what extent does, how well resolved your spatial discretization is in the model? How does that affect the results we get? So what we've been working on over the past 2 years, really, since the geometry, the design of the car was frozen, is a sampling of that uncertainty space. So we define our uncertainty space based on all the things that we know affect the model results. We use some kind of statistical sampling method, like Latin hypercube sampling, to sample that space to try and understand the sensitivities of the results, the lift drag coefficients as a function of Mach number, pressure distributions over the surface of the vehicle as a function of this sensitivity space. And what's interesting as being a kind of a new way of thinking for me as an academic is we've used that information, or the early results from that work, to decide where we're going to collect data from the vehicle. Now, as an academic, if you've got a problem like this, where you've got kind of uncertainty in your modelling, and the goal, just with your academic hat on, is to get the paper published, you then go, we'll place the sensors to collect data at positions across the vehicle where we're fairly convinced the model is doing a good job. That will get me to the point where I can write a nice paper. Now, in the real world, where you're putting your friend in a 1,000 mile per hour car, you do the complete opposite. You cluster your sensors in regions of the car on the surface where this sensitivity analysis is showing at these positions on the car we have the greatest level of uncertainty in the modelling. And that's where we want to learn as much as we can, therefore that's where we're going to try and glean as much data as we possibly can. So the clustering of the pressure sensors, and there are 250 sensors across the surface of the car, we'll start getting data from in October, and then meaningful data at high speed next year, are all clustered around regions where, I guess in simplistic terms, the standard deviation in our modelling results are the largest, i.e. we have the largest uncertainty units. It's a pretty pragmatic approach, but that's the approach we've used in terms of how we cluster these sensors to acquire data. And then one of the things we're realising, and this is really going to be the main thrust of the second part of what I want to talk about, is we're trying to think hard about how do we now engage humans in this kind of data visualization, data acquisition, decision-making approach. Because after every run of the car, we're going to have a whole lot of data from pressure sensors off the vehicle. We've got an awful lot of data backed up from CFD models that have run. I guess we're now entering into the regime of big data, whatever that is. And we're starting to ask questions about how do we, in a meaningful, intuitive way, allow design engineers who may not be CFD experts, they may be aerodynamicists with no CFD experience, who will be sat at the side of the desert after a run. How do we meaningfully allow them to engage with the CFD results, data from those pressure sensors, and try and identify where those two sets of data are mapping well, where they're not mapping well, which models would be the best ones to use to try and predict what will happen on the next run of the car. One of my MSc students here, Chaluba, has been working on the software that we're going to be using for that over this summer. I'm not going to be here this afternoon because we're off to Bloodhound to meet with the chief engineer and the systems engineer to talk through that process. Another thing that we think is going to be really powerful, which I won't talk about too much because Bob Laramie is here and I know that's going to be a big part of what he talks about later, is in terms of visualizing this complex CFD data, what's the most efficient, effective, and quick way of doing that? Because what we might want to do is we interrogate the data we get from the car, we compare it with our CFD models, we find regions where there are unexplained behavior that the models weren't predicting. What I would like to be able to do is very quickly then go, well, let's have a look at that data, let's visualize the flow in that regime, to have a look at what the model was doing. And kind of my understanding, or a CFD expert's understanding of how CFD modeling works and the kind of approximations you're making in a RANS model might allow you to say, okay, it's because the model was predicting this. We know in reality, because we just witnessed it, something different was happening. We understand that well enough to make a decision that running the car faster is safe, even though the models and the data from the car were diverging at that point. But I'll let Bob talk a little bit more about the actual processes for doing this data visualization. So in terms of the testing of the car, I guess that's our pragmatic approach to dealing with the uncertainties we have. The second part of what I want to talk about is how we've dealt with some of the ideas that we're now working with in terms of decision making in the design process where you have uncertainties. It became quickly apparent to me over the years that we've been working on this that there have been very much two parallel approaches to design problems in aerodynamic design. So a lot of the time, as we've been evolving the design of the car, essentially what we've done is run a suite of CFD models, I create a PowerPoint presentation, meet with a bunch of design engineers, do the presentation, we argue around a big table, talk about what kind of geometric changes should happen in the next configuration of the car, and we move on. The design decisions have been primarily driven by human experience, intuition, through analysing data. But some specific kind of, particularly where it was easy to kind of neatly self-contain a design aspect on the car, so for example the fairings that wrap around the rear wheels of the vehicle, or the area distribution through the intake duct, which was work we did in collaboration with Rolls-Royce, we were able to set those up as self-contained optimization problems and basically throw them at some kind of computational optimization method and let the computer make those decisions for us. Now, I'll tell you a little story that kind of gets us to just play that while I'm talking about this. So at around this time, 2 or 3 years ago, I had a PhD student who was working with me, looking at novel computational optimization methods. The kind of problems he was solving were relatively simple, 2D aerodynamic optimization problems like the inverse design of an aerofoil. You give a known pressure distribution over an aerofoil, can you find the geometry that gives you that pressure distribution? Using evolutionary methods, population-based optimization methods, where in each iteration of the design you're testing a family of designs, a population of designs, rather than a single design that's evolving, as you would in a gradient-based method. So he's doing this kind of work, and this is interesting, and we're looking at how these kind of evolutionary algorithms behave and how designs cluster at different points in the design space, and so on. And at the same time as all of this was going on, I found myself in the coffee shop at the university, because that's what the PhD supervisor does. He sits in the coffee shop and the PhD student does the work. That's not true. But one of the reasons I love working at university is because you have these weird encounters with people from very different disciplines. So I was sat in the coffee shop, a colleague of mine grabs me and says, there's this guy over here, you need to come across and meet him. I've been meaning to get you two in the same room for a long time, and you're in the same room, let's get you hooked up. And it turned out that this guy was one of Bob's, I don't know if he was a PhD student or a postdoc of yours, Matt Edmonds. He was a PhD student at the time, doing a PhD in data visualization. So pulled him across, and we sat down, had a little chat about what we both do, and he said, oh, that's really cool, because one of the things that we've developed is methods for visualizing CFD data. Any chance I could have some of your data sets to use as an example? And I said, yeah, brilliant. You know, one of the frustrations I have is how time-consuming it is using kind of commercial packages or things like ParaView for doing CFD flow visualization. So he said, well, no problem. You send the data across to me, I'll have a play with it, see what I can do. So later that day, I sent him across some links to download these CFD data sets from simulations of Bloodhound, with some explanation of how these data sets were configured. And literally, within a couple of hours, he was emailing me back pictures that looked like this, which, first of all, were far prettier than anything I could produce in ParaView or Insight or anything like that. I was amazed how quickly he had done it, because for me to be able to do stuff like this, where you're trying to figure out where you seed stream surfaces and so on, is just a pain in the butt and takes a long time. I mean, he basically just asked me a few questions, like what kind of things are you interested in? I said, well, I guess identifying flow separation, vortex shedding, presence of shock waves, pressure distributions. Those are the kind of things I'm generally interested in looking at. And I started getting these things back. And that's when we had what I hope is one of our great ideas. So I was getting frustrated that there were these two parallel approaches in our approach to designing the car. One was this purely computational world, and one was this world where we sit down and we explore ideas and we use human experience to do the design. And I started thinking, well, what if you could combine those two ideas together? So we've started a project now which I'm referring to as non-artificial intelligence. The other term, I guess, is human-in-the-loop design. People think, I think funding applications for non-artificial intelligence sounds a bit better, which is why we're using that term. So we're using a combination of, I guess, interesting hardware, like interactive screens, and we're trying to think about the best ways of presenting data back to a human designer, which explore things like how are your designs, because in these schemes we've got populations of designs evolving with each iteration. So how are those designs moving through the design space? How do we show that in a meaningful way to the design engineer? How are, for example, the fitness or how the objective function of your best design or your worst design evolving with iteration number? Again, how do you most effectively represent how designs are clustered across a high-dimensional design space? Once you're above about 2 or 3 dimensions, in terms of the degrees of freedom in your problem, it's very difficult to intuitively show that. And what we're looking to do soon is incorporate automated flow visualization into this, so that as these evolutionary optimization systems, which, you know, for a complex 3D problem with many degrees of freedom, might run for 2 or 3 weeks to solve, you know, industrial scale problems. Well, what if we could develop a system where every morning a design engineer gets into work, fires up his screens, gets automatic information about how the optimizer has been evolving in the runs it's been doing overnight. You can select designs within the design space and automatically get some flow visualization sent to you to help you make decisions about things like, can we trust the solutions at that point in the design space? One of the things that we use within these schemes is reduced order modeling to accelerate the process, which kind of lend themselves naturally to population-based optimization. But quite often, you've got to ask questions about whether you can trust those reduced order models. And perhaps a human being who can look at those solutions and go, I don't think the reduced order model is getting that right. We need to run that again as a full fidelity model. Those kind of questions could be answered in real time as the optimizer is running. So these are the kind of ideas we're exploring at the moment. And we started applying these to now a kind of a whole range of industrial applications. So we're working with a small aerospace company, helping them design this small aircraft. We're currently doing a project I can't tell you too much about, with UQ&M, where we're looking at winglet optimization. And interestingly, we've just started a PhD program working with a marine company, so we're now kind of moving into a new sector. It was really interesting. We started showing them some of the results of our simulations where we were trying to model dynamic response of boats as they go over, high-speed boats as they go over waves. And not only did we have kind of marine design experts in the room, we had high-speed motorboat drivers in the room. So we were showing them how the design had been evolving within the optimizer. And he was able to say, that's just not how a boat would respond. I can see why the model is predicting that. In reality, this is what would happen. We could say, okay, we can tweak the model in real time. As we keep moving the design process on, we'll tweak the model and try and incorporate that kind of physical phenomenon. And we're trying to move these. At the moment, we've looked at relatively simple, self-contained problems in terms of geometrical complexity, and what we're looking to do now in the next few years is extend it to kind of more geometrically complex problems. So in the context of aerodynamic optimization, I guess this is the hypothesis that the work we're doing at the moment is trying to test, that human experience and intuition effectively integrated into the computational aerodynamic optimization can be more powerful than either approach in isolation. And as I've said, this is very much a work in progress. We're very keen to look for other collaborators, so if you've got problems that you think maybe these kind of approaches could solve or we could use as interesting test cases, we'd be very keen to chat to you. But I will stop there and invite any questions.
Thank you very much. Yeah.
The human user,
Yeah.
how are you capturing the uncertainty in the human user and the dynamics that comes into play? And is there a system emergence between the human driving user and the aerodynamics?
Yeah, that's a really good question. It almost becomes a psychology problem then. So, I mean, the reality is we're not far enough down the road to do a scientific study that looks at to what extent, you know, different human interactions affect the outcomes. That's something I would like to do.
Are there tools that help to facilitate that?
Pass.
Oh.
I don't know.
Any more questions? We've got 3 should take first. Chairman's broke too, but that's not standing.
Interested in the sensitivity analysis as well, because I guess different parameters play a different role at the different phases, whether you're transmac or subsonic.
Yeah.
So do you take that into account as well?
Yeah. So we can look at, when we're testing the car, we run these studies. We tend to pick 4 Mach numbers that we think are interesting: 0.5, 0.8, 1.1, 1.4. And we'll do that sensitivity analysis at those different Mach numbers. And yeah, you're absolutely right. You will find that the sensitivities are different in those different phases. But what we can do from that understanding is, when we're moving through those different phases, say, well, we know that this is probably the most trustworthy model at this point, so we're going to choose to compare our data, or primarily rely on that model when we're predicting what's going to happen if we go 0.5 Mach number faster, and so on. And the more complicated one is, which I think we will encounter when we start getting data back, is I think different models will do a better or worse job at different regions across the surface of the car. So I think particularly underneath the car, where we've got huge levels of uncertainty in what kind of surface is that? Once you start generating that bow shock, is that even a surface that can be defined in a meaningful way at all? Is it predictable, the amount of particles that are being entrained underneath the car? So I think it might be that different models predict what's going on underneath the car compared to over the fin, for example, where you might just standard, no particles, standard Rand's model does it best. So that'll be a tricky thing if we find that different models at different certain regions of the car are more trustworthy.
Mark? Yeah, so in terms of the stability of the vehicle speed, are you fundamentally looking for areas of high pressure and areas of low pressure and the delta between the two? Is that what causes the instability?
Essentially, it's those the net loads and the way those forces are distributed across the vehicle to define, your standard things now, like static margins and so on, that define the vehicle stability. That's what we're working off at the moment. In terms of the actual dynamics of the vehicle, at the moment everything we run is static, assumes we've got a static model. When vehicle dynamics is built into this, it becomes a whole lot more complex.
Yeah, I'm talking to a couple of people at Brunel, and they're working on aerodynamics of truck trailers.
Right.
And obviously the weight causes a lot of drag.
Yeah.
They're working on some kind of porous material which, if you like, connects the high pressure to the low pressure and allows.
Yeah. So effectively we're doing that by basically blowing out all of the air that goes into the engine bay out the base of the car to try and reduce the base drag as much as we possibly can. So it's the whole, and again, how well we're approximating that in the CFD model is a big question, because it's difficult to model that. So we make some assumptions about to what extent the predictions on the base of the car and the model can be alleviated by blowing air through the base of the car, and there's uncertainty.
I've got a couple more questions. Just one more.
I've got a question about the data flow visualization.
Yeah.
What kind of understanding we can have out of those pictures?
Yeah, so I mean, at the moment, the thing that we're primarily focusing on, but there's a lot more that we could do, is changing the design space in real time. So one of those plots shows you, so at the moment, I think the highest degree of freedom problem we've run this on was I think 8 or 9 degrees of freedom. And you can represent that design space in some way. There are various ways of doing this. And you can look at, okay, over the last 20 generations of the optimizer, this is how the designs have been clustering, or they've been clustering in this region. Now, someone with experience and intuition can look at that and go, okay, aerodynamics, I can understand why you're clustering here. Or you can look at degrees of freedom that don't seem to be very sensitive. So you could say, well, there doesn't seem to be any clustering on this particular degree of freedom, which potentially implies that degree of freedom isn't important. So maybe we can take that out of the design space, make the design space smaller, and help the optimizer find the optimum of the other degrees of freedom. Or if the optimizer is moving towards the boundary of the design space, and it seems to want to go outside of the predefined design space, in principle, you could in real time just extend the size of the design space and just say, okay, well, if the optimizer wants to go there, let's see what happens if it does go there. So those are the kind of things we're playing with at the moment, kind of real-time kind of changes of the design space, adding in, taking out degrees of freedom in the kind of geometric descriptions. Those are the kind of things we're looking at.
Jamie, you had a question?
Oh, yeah.
Still got a question.
Potentially something you've already looked at, but in terms of the positions of the sensors,
Yeah.
You want to record the most sort of informative points when you do the physical testing. It might be worth, if you've not already looked at it, looking at the different acquisition functions you can get from Bayesian optimization literature, rather than just the max variance of point.
Okay. No, that isn't something we thought about. So we should probably have a
Maybe
conversation
before
at a coffee break. Yeah, if you could point me in the direction of something that would... I mean, the reality is, for this first year of testing, this isn't entirely, so we fixed the position of 180 of the sensors, we've got another 70 to play with. So if there are things you can point us towards that would give us, help us make the most useful decisions about the remaining 70 should go, then yeah, certainly.
We probably only have time for one more question. You're around for break?
I'm here till after lunch.
Yeah, okay.
Which relates to Joe's question, really. I mean, you identify the location or the potential locations where uncertainty exists, so you would like to reach the information there. Do you consider any uncertainty whether this location is exactly there, place in it, and whether in how much the flow is affected from the sensors that you use?
Yeah, that's a good question. I guess the easy answer is no. The assumption is that when I'm told this is where the pressure sensor is, that is where it is, and I can map that directly back to the model, and the pressure value I'm getting from that sensor is the pressure at that point. So there's uncertainty there as well. How you deal with that, I don't know. Great.
Wonderful. Thank you very much. So our next speaker is Dave Wood.